Good evening, physics students. I wanted to take a moment today and talk to you about what exactly it means for something to be kinematic. And the thing that we need to take away is that kinematics are nothing more than situations in which linear motion is moving at a constant velocity. The thing about moving at I apologize, not a constant velocity, a constant acceleration. The thing about objects moving at a constant acceleration is that their motion is predictable, and we can solve for those mathematically. So we really focused in on talking about the conceptual side of motion. We want to show you now the mathematical side of motion as well. In order to do that, we're going to relate it to graphing, as we've been focusing a lot of time on that. And the first thing that we want to bring up are position time graphs. We've already shown you the equations for these, and you've seen them on your equation cards, but we're going to take a moment and talk about how they truly relate to what we're looking at. And the first situation we're going to look at is when acceleration is equal to 0. The equation we're going to focus in on is our displacement equation. X equals x naught, so final position equals initial position plus initial velocity times time plus 1/2 at squared. And we already said that acceleration is going to be equal to 0. And with that being the case, we can get rid of this back half portion. If we break this apart and we're looking at a position time graph where x is the y-axis in meters and time is in seconds, we've already said that acceleration is going to be equal to 0. So we're going to have a line with a slope. If you recall, a line with a curve on it is where we have that situation in which we have acceleration not equal to 0. So if we translate that over, we can actually rewrite this equation into something you are very familiar with, and that is y equals mx plus b. That's an equation when determining slopes you've used in algebra, where b is the y-intercept. Notice if we're starting at the point of reference on a position time graph, our y-intercept is technically and typically 0. However, if we move that up, our y-intercept is no longer 0, so we would need to plug that in to find out where we're going to be at a certain point in time. The x-axis is time, and the slope of a position time graph is equal to the velocity. So these translate really, really nicely. And if we have a scenario where a is not equal to 0, that's where we get that t squared coming in. And we end up with a pretty significant curve on our graph. The other equation that we're going to look in on is, in terms of graphing that is this equation here. Vx equals v naught plus at. All right, and I put the x there because we're going to be looking at it in terms of the x direction. So we have Vx equals v naught x plus at. Again, we see something very similar, y equals mx plus b. These are going to relate to a velocity time graph. Here, again, same thing, we're reading graphs. If we've got time here, velocity in meters per second here, we can't have a curve on a velocity time graph that indicates a changing acceleration. That is not kinematic motion. So we end up with, again, we can have a similar line like so based off of plugging in our numbers. So how can we break this down? Well, this equation here can answer the question, how fast is it going? And our equation on this side can answer, where is it at? So if we have enough information, we can solve for those two questions that will help us out. But there's a third equation that we're given. And so let's really set out these three equations, and that should give us a general idea, and we can try to come up with a solution to how to use each equation, or when to use each equation even. The algebra, I'm pretty confident that we can come up with on our own, but let's talk about how and when we can use each equation. So we'll put the equations here first. And we're going to take a look at it in terms of the variables in the equation. And in physics, especially kinematics, we're going to call these the 5 golden variables. Because these variables show up within these problems, and they're the ones that if we're solving motion, we are most concerned with. So let's go ahead and take a look at first here this equation for a velocity time graph. Vx equals v naught x plus at. Well, I'll tell you what, let's go ahead and just iron out all of the equations then. And these are on your card, so don't feel like you have to write them out, but they are located the first 3 equations on your AP Physics 1 test card that you received at the beginning of the year. And then finally, the equation that we have not used yet that will help us determine out some information. So the 3 things that the 5 golden variables that we're going to be working with. We have final velocity, we have initial velocity, we have acceleration, we have time, and we have displacement. Now remember, displacement can be written as final x minus initial x will get us that displacement. So if we take a look at each of these equations, we can really take note and view the scenario that we're given. So let's go through and let's mark each of the variables we're given in the equation, and that should help us determine which one we're going to be working with. So if we take a look here at this first one, we're given a Vx, we're given an initial velocity, we're given an acceleration, and we're given time. What we're not given is that displacement. So the name of this equation is going to be the no displacement equation. And what's really nice is that there's no guessing on which equation we're going to use. You just go through, find out which one you're missing, and that's what we're going to focus in on. Here we're given x and x naught, so we are given the displacement. We're given an initial velocity, time, and acceleration. This is absent of the final velocity, so we're missing Vx, so this is the no final velocity equation. Again, pretty nice in terms of picking out which equation we're going to use. Finally, we're giving that final velocity, initial velocity, acceleration, and displacement. We're absent time, so no time equation. What that's going to allow you to do is really lock in on which of the following equations you're going to want to use. So we're going to go ahead and do an example problem together, and you'll need to click on the next video for that.